I give you another opportunity to ask questions if you have any. Otherwise, I will go to the next point. All right. So the next point is, I promised you to basically show you the general derivation from where this Hamiltonian comes from, this S dot S. Because when you first see this, the naive somehow expectation is that this just describes the interaction of magnetic moments. Yeah, so kind of like a naive thing like V dot S, you know, the coupling we have in quantum mechanics. So interaction of magnetic moments, but this is wrong. There is such an interaction in magnets, but it decays very, very quickly with distance. Yeah, so the origin of this Heisenberg exchange interaction is very different. So where it actually comes from, and that's what I will show here, it's actually a consequence of the Pauli principle and strong interactions. And to understand this, what I will do is I will derive for you this Heisenberg model as a strong coupling limit of the Hubbard model. Okay, and so what is the Hubbard model? Okay, so the Hubbard model is the standard model for interacting electrons in a conductor, so in a metal or in an insulator. So let me first of all write the Hamiltonian. So what you have there is you have a tight binding model, so just electrons. And I should say the specific derivation I'm going to show you now, I will just do for a one-dimensional model, but exactly the same calculation holds on any lattice, in any dimension. Yeah? It's just for notational purposes, so it's completely general. And I should say this idea of a strong coupling expansion, so if you don't have a small parameter, but if you have a large parameter, it's also very general. Yeah? And so this method here is much more general than the particular case I consider. Okay, so I consider this tight binding model of electrons, so just a single band, J sigma, sigma plus 1 sigma plus an initial conjugate, and then I have an interaction term. So what are these? So these CJs are two species of fermions, electrons. So they carry spin up or spin down, as electrons do quite often. And we describe them by these canonical Fermi operators. They fulfill canonical anti-commutation relations. Okay, so this would just be a free theory. So this would be a single band of electrons. Yeah, so in momentum space, just would give you some dispersion. That's okay, and would be described by band theory. So this is where the interest comes from. So nj sigma is a number operator of electrons with spin sigma. And physically what this term means, if you have two electrons being at the same site, it costs an energy U. So they repel each other. And okay, where does this model come from? Well, okay, so what you know is if you study conduction in solids, you usually start with band theory. You would have a band of electrons which interact by Coulomb interaction, which is long range. Yeah? But then typically there's something called screening, which tells you the actual interaction these electrons feel is really not long range, it's short range interaction. And a cartoon for that would be if you just take the local interaction into account, if you have two electrons sitting at the same side. And the side you should think as the location of some ion. Okay, so this is a standard model of interacting electrons. And its physical origin should be kind of apparent, unlike this exchange interaction where we want to get. Because these are essentially, okay, so think of it like this. This is some potential where you have some ions sitting. This would be your lattice of sides, and then you have electrons which can tunnel from here to here, or from here to here. So that's described by this term. That's a tunneling term. Electrons tunneling from one ion to the next one. And this would be some characteristic scale for the strength of this tunneling. And then this basically would express if I want to tunnel from here to here, but there's already an electron there, they repel each other very strongly because of the Coulomb interaction. It costs a lot of energy. So you suppress such tunneling. Yeah? So here, physical content should be here. All right. Now, why is this model interesting? Well, it's very interesting because, let me just briefly do this. It's the simplest example where you have what's called a Mott transition. So, what is the physics if I have U equal to 0? So let's say U equal to 0 and half filling. Half filling is 1 electron per side, on average. Yeah? So the electron number commutes with the Hamiltonian. It's a conserved quantity, so let me just fix it to be the same as the number of sides. Okay, what is the physics in this limit? That's a question to you. I don't know really you want to talk about. Bruno, you at least will know. Otherwise, I can later. No?
You didn't catch the question. Sorry.
Well, the question is, what is the physics if you don't have interactions and 1 electron per side?
That's 3 electrons.
Yeah, okay, it's 3 electrons is a metal.
Yeah,
it's 3 electrons, not interacting electrons. Exactly. So here, this is a metal. Yeah, because what you do is you can solve this just by going to Fourier space. In Fourier space, you get a band, and the band cuts energy 0 at momentum in 1 dimension pi over 2 and minus pi over 2. Yeah? So you have electronic excitations which show cost energy, and they can carry current. So this is a metal. So if you put a voltage, they just go. Okay, so now the other limit would be t equal to 0. Yeah, and u larger than 0. Okay? And so what is the physics in that limit? The physics in that limit, I have a classical Hamiltonian, just this one here. Okay? And the lowest energy states will have precisely 1 electron at each side. Because if I have precisely 1 electron at each side, not on average, but precisely, it costs 0 energy, which is the smallest you can have. Okay? On the other hand, then these electrons, they can, there are many degenerate states, yeah? Because you can have spin up here or spin down. So at each side you have a degeneracy because spin can be up or down. So there are 2 to the L states. But none of these 2 to the L states can conduct charge. Yeah? Because there is no tunneling. Yeah? So the charge is frozen. So this is an insulator. Yeah? Obviously, you will say it's an insulator. It's not a big deal. All right? Okay, but that means now, as a function of u over t, there has to be a phase transition between a metal and an insulator. Okay? So, or u over t or t over u, so let's do t over u. So, when this goes to 0, it's an insulator. And if it goes to infinity, it's a metal. Yeah? And in between, there has to be a transition called the Mott transition, which turns a metal into an insulator. And what's interesting about it, it turns a metal into an insulator because of interactions. Yeah? Not because it's a stupid band structure, it's a band insulator, which is boring. That would be a free theory. So here, interactions, electron-electron interactions, turn the system insulating. Okay? And so that's very interesting. And how they do that is a big question to answer. All right? And in high-energy physics, you have exactly this analogous phenomenon where interactions basically turn a gapless state into a gapon or metal into an insulator. It's called dynamical mass generation in that case. So this is the same as dynamical mass generation in high-energy physics. And so this model is the simplest paradigm for this phenomenon. Yeah? Okay. Now, where does the Heisenberg model fit in? The Heisenberg model fits in by starting here, in this limit, which is called the atomic limit, yeah, where all your electrons just sit at the sides and don't move. Okay? And now, we look at that limit a little bit more precisely. And then the Heisenberg model will emerge as described in the dynamics in that limit. So, now, what does the spectrum actually look like in this limit? Let me start with that. So let me plot here. Well, you can just plot here momentum. It doesn't really matter. Here's energy. So as I said, the lowest energy states live here at zero energy, and there were 2 to the L of them, which was just the spin degeneracy at every side. Okay. And then what I can do now is I can, instead of having 1 electron at every side, I can take one of them and put it on another side and make a double occupancy, a single double occupancy. And all the other ones I still keep separated. So that would cost energy U. Yeah? And you get a certain number of states here as well. So we have such a thing. And then you can make 2 double occupancies or 3 double occupancies. Yeah? So that's what the spectrum looks like. And what I want to describe next is, that's in the limit when t is equal to 0. So now I want to take t into account. Okay? And what will t do, this hopping term? It will actually remove the degeneracy in all of these subspaces, first and foremost. Yeah? So this gap here is still very, very large. Okay? So if t is much less than u, essentially what t will do, it will remove the degeneracy, so you get some kind of like fuzzy thing here, and some fuzzy thing here. So the width now will be something like 4t here, or something like this. We'll scale with t. Yeah? But it will not destroy the structure of these of the spectrum, which is still banded in this sense. Okay? And where the Heisenberg model will arise, it will actually describe what happens in this low energy subspace. It describes the physics of this low energy subspace. All right, so that is what will be coming out. And in order to do this properly, so I'll develop a little bit of a formalism, which, as I said, is very general. You can use this for all kinds of other examples. So, let me start. So on each side, let me first write the basis of the Hilbert space. So I would have empty side, electron spin up, electron spin down, and doubly occupied. Did I do this correctly? Up, down. Yeah, so I call this 2. Yeah. And so be careful. Yeah, so one of the standard mistakes people do when they kind of like play with these things, the order of how you define the doubly occupied state matrix. So I defined it as C dagger J up, C dagger J down on the vacuum. Yeah. So in other words, the up spin is to the left. It's a convention, yeah, but you have to stick to your convention. And if you don't, you get some signs wrong. So if you get some unreasonable signs in one of these calculations, well, this is what you did wrong. So now define Hubbard operators. On side J, and these are simply one-dimensional projectors on these states. So this would be AJ, BJ. Yeah? And AB run from 0 up down to. Okay? So I just defined some operators which now work on this side. Now you can check very easily that they fulfill an algebra, so they close. Yeah? This is also not surprising. And the algebra is simply xj, AB, x, okay, so I first should do it like so, n, CD, this would be xn, CD, xj, AB, minus 1 to the epsilon A plus epsilon B, epsilon C plus epsilon D, if j not equal to n. Okay, so now where does this come from? It comes from the fact these operators can be either bosonic or fermionic. Yeah, because this state is bosonic, it's empty. This state is fermionic. This state is fermionic. But this state, once again, is bosonic because it has two fermions. Okay? So if I define these Hubbard operators, they can now either be bosons or fermions. Okay? So if you have the same type of state here, either bosonic or fermionic, then the operator will be bosonic. But if you have a fermionic here and a bosonic here, the operator will have a fermionic nature. Okay? And this then simply says bosonic operators at a distance commute, but fermionic operators at a distance anti-commute. Yeah, that's all. And the algebra I was talking about now happens on the same side, so xjAB, xjCD is simply xj, let's do it like this. How do I, no, I didn't, just a moment. Sorry. xjAB, xjCD, something like delta BC, xjAB. So you get some algebra of that kind. And this simply comes from the fact that you have these one-dimensional projectors. Delta BC, yeah, that's right.
I still have a basic question about the model.
Yes?
Because, so there's no term in the Hamiltonian that can change the spin up to the spin down.
No?
So then I just, if you say the ground set has 2 to the L degeneracy,
Yes?
then you don't think about the fixed number of electrons. And
Yeah, okay, so now it depends, okay, it's a good question. I mean, so what I was saying, I was just looking at the spectrum of energy eigenvalues. Yeah? And as far as energy eigenvalues are concerned, there are 2 to the L states which have exactly the same energy, which is 0. Yeah? And the degeneracy comes from the spin. Yeah? So as far as these are just states in the Hilbert space, right? So as far as these states are concerned, the state with all spins up has the same energy as the state is all spin down. And if I wanted to remove this degeneracy, so put a chemical potential, so to speak, that would be a magnetic field, but I'm not imposing this. Yeah? And what you will see is once we take the tunneling into account, yeah, this degeneracy will be removed. And you will actually find, I think this is where your question comes from, you will actually find that the ground state, the lowest energy state, is a spin singlet, as you might have expected. So it comes from the tunneling. So the tunneling basically then selects the state where, which is a singlet state. Yeah? But at this level, in a sense, we're not working in an ensemble. I could work in an ensemble, yeah, where I fix the number of up spins and down spins separately. But it would be a grand canonical ensemble, yeah, where the Lagrange multiplier I need to fix the spin would be a magnetic field. That would be the physical content. Yeah? So I would have to study the Hubbard model. Blah, 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 minus BSZ. That's the model I would have to study. Okay? But then physically what I would do is I would have to study a situation where I actually have applied a magnetic field, which is not what I want to do. Yeah? So it's physically a different situation. Yeah? So, and I want to actually study this one. Okay?
What is epsilon?
Epsilon. Okay, epsilon is defined here, so epsilon 0 is 0, epsilon up is 1, epsilon down is 1, and epsilon 2 is 0. It basically is the grading of the algebra. Yeah, it tells you whether you have trouble. Thank you. Okay, now, no, I have another half hour, right? Mm-hmm. Yeah, okay. Now what I want to do is I'm going to rewrite my Hamiltonian in terms of these Hubbard operators, but in a very particular way. And the way I rewrite it is like so. H Hubbard is U times D hat. So that's the interaction term. Okay? And what the interaction term actually does, if you think about it, it counts the number of W-occupied sites, which that's why I call it D hat. It tells you how many W-occupied sites you have. And then I say here now, T hat 0 plus T hat 1 plus T hat minus 1. And these three operators, let me first tell you, well, what I do. The structure of the spectrum I've shown you here was such that the spectrum was organized according to the number of W-occupied sites. Yeah? 0, 1, 2, 3. Now the hopping term, yeah, in the Hubbard model mixes it violates the number of W-occupied sites. Because it can take one and make a double occupancy or destroy one. Okay? Now what I do is this hopping term, I split it up into three pieces. Yeah? One piece is a hopping that leaves the number of W-occupied sites the same. One that increases the number of W-occupied sites by 1. And one that decreases the number of W-occupied sites by 1. There are only these three possibilities. So I must be able to decompose the hopping term in this way, and I can. And the answer is like so. It's actually straightforward to work this out. Let me first write it down. Sigma, this is correct. Xj 0 sigma, xj plus 1 sigma 0 plus xj 2 sigma, xj plus 1 sigma 0. So this, I claim, corresponds to hopping processes which leave the number of W-occupied sites the same. So let's check. So this one would only work if I initially have a state sigma at j plus 1, and I turn it into a state, and I have 0 at j. Yeah, that's initial. And then final is the other way around. So I have sigma 0 j plus 1. So it essentially describes the hopping of a spin sigma if the neighboring site is unoccupied. You can just read it off because once again these are projection operators. This is how it works. And the others, so this would essentially be hopping of the spin in the opposite direction, and this would be, you have a doubly occupied site next to a singly occupied site, and you move one of the electrons. But the number of doubly occupied sites remains the same. Okay? And now the others are like so. T hat 1 is minus J sigma x0 up, x0, oops, x down, it's just 2 down, sorry. J plus 1 plus x2 down, x0 up, minus x0 down, x2 up. And then I have one more, minus x2 up, x0 down, j plus 1. So that would be all the hopping terms which make an additional double occupancy. And so, for example, look here. So this is j plus 1. So originally I have down, up. Yeah? And then I hop it to 0, up, down. Yeah? So it basically corresponds to a process where I hop this one up here. Yeah? Okay, so, and t hat minus 1 is just t hat 1 dagger. So I can do this. Yeah.
Why don't you have sigma 2, 2 sigma in?
Sorry?
T0.
Yes.
Don't you have sigma 2, 2 sigma?
Sigma.
Just like you had 2 terms for.
Yes, yes, yes. I just didn't write it. So that's absolutely right. So plus x sigma 2, x2 sigma. You see, the blackboard is too small, which is why. Thanks. I mean, this the Hamiltonian better. Yeah, okay. Right. Hamiltonian better the Hermitian, right? So, thanks. Now, you can easily check, although this is kind of obvious by construction, that these operators have nice commutation relations with this d hat operator. It's kind of clear, right? Because this always counts the number of doubly occupied sites, and these change the number of doubly occupied sites. So you should have this algebra. Okay, now what we want to do is the following. So this is my Hamiltonian. Okay. So here in this Hamiltonian, I have parts which act in the same subspace of energies. And then it will have off-diagonal pieces which connect these different subspaces. Yeah? So the Hamiltonian will have blocks on the diagonal, which correspond to essentially how it acts on a given subspace of energies, yeah? Low energy states. And then you will have off-diagonal parts which connect them. Yeah? And what we want to do now is we want to do a basis transformation, so we want to do a unitary transformation, so where we remove in an iterative way the off-diagonal parts. That's the idea, so that we end up with essentially a block diagonal Hamiltonian in some sense. So let's see how we do this. So I do a unitary transformation, so just a basis transformation. E to the is h Hubbard e to the minus is. So all of this is, it's the same Hamiltonian in different bases. Okay, so this I've done anything. But now what we do is we essentially will use the fact that we have a small parameter, which is t over u, to choose this guy in a very clever way. So, what is this? So this is h Hubbard plus I s h Hubbard minus a half s s h Hubbard plus dot dot dot. Yeah? Just working out the first few terms. So now the idea is to choose S as a power series. Yeah? And then, if you look here, this is very large because it's proportional to U. These are small, they're all proportional to T. Yeah? So now, if I do my unitary transformation, I have such a parameter which is T over U. If I combine this T over U with this U, I can make a contribution which scales like T. And I will choose this in such a way that I kill the terms I don't like, which are the off-diagonal pieces. And the nice thing about this is this has nothing to do with just the first order kind of calculation. So you can carry this calculation to very high orders. Some people do this to order 22 or something like this. Yeah? And there's a price to be paid, which I can comment on, but this is a systematic procedure. Yeah? But of course what you have to keep in mind is in practice, what you will do is you will always keep a finite number of terms here, yeah? And anything you calculate in a scheme that involves such a unitary transformation idea, it will be some asymptotic series. So you shouldn't think that what you do here gives you a series in any sense that has a finite radius of convergence. It doesn't work like that. But this is also not what we need. So, H prime over U. So now I substitute this back in here and work out what H prime is. So this is T hat plus T over U. And here I have T hat 0 plus T hat 1 plus T hat minus 1. But I also get a piece plus I S naught T hat plus T squared over U squared, and here we get I S naught T hat 0 plus T hat 1 plus T hat minus 1 commutator. Oof, I don't know, that's a lot of terms, alright. Plus 1/2 I S naught with I S naught E. That's it, yeah. And then we have one more, which is I S1 with D. Plus dot dot dot. Okay, so you just formally plug it in, and all I've done here is I have collected terms of the same order in our small parameter. Okay? And now comes the point. What we want to do here. So I want to choose S naught in such a way that this commutator precisely cancels these two terms which I don't like. Yeah? And you can just basically read this off. So now choose, okay, so choose S naught such that T hat 1 plus T hat minus 1 plus I S naught D equal to 0. And the job that does it is simply T1 minus T minus 1. Because of, I erased it, the commutation relations of the T's with the U. Okay, and so then this leaves us now with some terms to order T squared over U squared here. Yeah? And those we still have to work out. So this leaves us with H prime plus U D hat plus T naught hat plus T squared over U. After the dust settles, T hat 1, T hat minus 1 plus order T cubed over U squared. Okay? And now, okay, so we still have to work out what this term is. That will be the Heisenberg term. but also it will be the Heisenberg term in a particular sense. Okay, so now let psi.
You remove this one from the.
Yeah, okay, so S1 is a good question, so I was skipping some steps because, what you want to do at this stage the same thing you did at this stage. So here there are some terms which you don't like because they're off diagonal. And you choose S1 in precisely such a way that you kill the terms that you don't want. It gives you another equation which fixes S1. And I have just written what remains. Yeah. And the calculation of S1 is a little bit messier, so I didn't want to go there. Okay, so let psi be a low energy state. So in other words, one of these 2 to the L states which were degenerate when t was equal to 0. Yeah? So then t hat on psi is equal to 0 because it doesn't have doubly occupied sides. Every side is singly occupied. And furthermore, t naught hat on psi is also equal to 0, as you can check by just going back to the definition of T naught. Okay, and then this leaves us with working out what this is. Yeah, and you see this is equal to minus t hat minus 1, t hat 1 on psi. Why is that? Exactly, yeah. There are no doubly occupied sides, which means if I act with this here, I will get 0. Yeah, so only the other part of the commutator actually contributes. Okay, so now we have to work this out, and to work this out, we go back to these Hubbard operators. So you now just express this in terms of these Hubbard operators. So this is then equal, okay, I might as well write it down, sum over j, 2xj minus sigma sigma, xj plus 1, sigma minus sigma, sigma here as well, minus 2, xj sigma sigma, xj plus 1 minus sigma on psi. Okay? And the final step now is these guys you can express in terms of spin operators. So now if you have an electronic model, spin operators are defined in this way. So Sz simply would be c delta j up, cj up, minus c delta j down, cj down. S plus j would be c delta j up, cj down. Okay, so what does this mean? The z component of spin is clearly the number of upspins minus the number of downspins. Yeah? And so this is just the number operator for electrons with spin up minus the number operator for electrons with spin down. And the spin raising operator clearly has to kill an electron with spin down and make one with spin up. Yeah? So this is just the realization of the spin algebra for spin-half fermions, spinful fermions. Yeah? And Sj minus just Sj plus standard. Okay, and now using this, you can convince yourself that this is simply equal to 4 sum over j, Sj plus 1 minus a quarter 1 psi. Right, and then finally, it tells you, this tells you that your effective Hamiltonian, which is what we have to write here, is actually a Heisenberg model. So H Hubbard on this manifold of psi states gives something like 4t squared over mu sum j is j plus 1 minus a quarter psi. And this is where this exchange interaction comes from. It's just a consequence of strong repulsion. Yeah. And as I said, so now you could carry this procedure further. So the next correction would be t cubed over u squared. And then t to the fourth divided by u cubed, and so on and so forth. And the nature of these terms would be, you can always express them in terms of spin operators. Yeah. But they will involve higher and higher powers of spin operators. Yeah. So the next one would involve actually 4 spin operators. And if you're on a 2-dimensional lattice or a d-dimensional lattice, it would correspond to ring exchange. So if you have a plaquette there, so it would involve exchange of spins around a plaquette. And the higher order terms would involve spin exchange around larger and larger loops on your lattice. Yeah? And what you also would find is coefficients here that multiply these terms. They are numerical factors which grow. Which basically tells you this is not a convergent series in any sense. It's some kind of asymptotic series. Be understood in this way. Okay. Finally, so I did this for fermions here, and I derived for you from this interacting fermion model this Heisenberg Hamiltonian where this exchange constant here is positive, corresponding to an antiferromagnet. Okay, which is typically related. This always arises if you have repulsive interactions between fermions. The same kind of analysis is quite interesting also for bosons, in particular if you're interested in bosons in cold atomic traps. If you have strongly repulsive bosons, you can go through exactly the same analysis. And the only thing that changes is you pick up an overall minus sign, having to do with bosons commuting rather than anti-commuting. So it basically means that the spin degrees of freedom for interacting fermions, they want to anti-align the spins. So you have this anti-ferromagnetic interaction, whereas for bosons, you favor ferromagnetism. I'm supposed to stop, I think.
More or less, yes.
Okay, so I will. Okay, so
Can you say one thing?
Yeah.
So this, so originally you think that this spin is degenerate.
Yes.
Then there is this Heisenberg interaction from the virtual process of one electron going to a next and coming back.
Exactly. It's a second order process. Yeah.
Yes.
Exactly.
And then it has to do with the fermion nature.
Yes. With the fermion nature, because it hops there, yeah, and for example the other one will hop back, but then these guys have to flip.
Yes.
Yeah. So this is how the statistics is felt. Okay. Yeah. So it's a virtual process. So physically, so what Andrea is saying, there's a physical explanation where this comes from. So your electrons always sit one at each side. Yeah. But now this spin here. Yeah, so now talk quantum mechanics, so we talk uncertainty relation. So this spin can go over here for a very, very short period of time, which is compatible with uncertainty relation. Yeah, and then one of the two can go back. Okay, so you end up in the same low energy subspace, but what can happen is, well, you take this one over, so then you have some virtual intermediate state where you have up, down, okay? And now, the other virtual transistor, now you take the down back, and you have the up here. So you end up with a final state where the spins have exchanged. Yeah? But you see, virtually, so for this short period of time, they were both at the same place, so they feel each other's statistics. And that's why bosons and fermions give an opposite sign. Yeah? But so this is the physical picture. All right. Thanks.
questions? Maybe then lunch. Okay.